a convenient time for, oh, okay, not, okay, I have this other computer that need me. Anyway, who wants to start? Yes?
Is there a way to turn that button on?
Oh, so the back, okay. Let's try, I will bring it down. Is it on?
Yeah, okay, that's good.
Okay, now I'm going to bring it back up because sometimes it doesn't start again. Is it okay? All right. What's that?
Turned down just a teeny tiny bit. It came back right at the end.
Did it really? Okay.
Yeah.
All right, okay.
Thank you.
No problem. I want you to be able to concentrate and be like, ah! Instead, yeah. Might be that way for other people. Anybody actually have any questions? Yes.
Could you talk about the large-scale structure of the universe in terms of superclusters and voids?
Why, sure, I could do that. Let me get this thing ready to show up each word. Let's see. Courses. Astronomy 111. 2017 spring. I mean, no, this is fall. Back in time. Share it with students. And let's see, I guess this one would be, is that, was that chapter 22 or 23, right?
20.
Which one? Oh, 20?
It was on a couple of them, actually, the same bullet.
Is it really? Huh. I'm trying to remember which, yeah, because it tends to blur sometimes. Well, I'm going to do it in chapter 20. So, the large-scale structure of the universe refers to the fact that if you look on very large scales, then the galaxies are not just distributed at random. Instead, they are concentrated into superclusters, and there are essentially strings of superclusters. So this is a map of the large-scale structure in some particular set of directions. The dots are all galaxies plotted with distance away from us here at that point right there. So what you can notice is that there are concentrations. The galaxies are concentrated in some regions, and there's almost no galaxies in other regions. So the regions that are kind of like bubbles that are nearly empty of galaxies are what we call voids. And galaxy superclusters form networks that are kind of like the walls of the voids. And so an analogy that's often made is leavened bread or soap suds or sponges. In each of those cases, you've got bubbles that are surrounded by sponge or dough or soap or whatever. And so the clusters are like that, except that it's individual galaxies, not continuous. And then the voids are the holes in the middle, so to speak. And the voids are something like 100 million light years across. So that's the idea there. And then, of course, we have to figure out, astronomers wanted to figure out where that comes from. Can we explain it? And as I showed a simulation in the last class, the answer is yes. If you start with concentrations of dark matter in the pattern implied by the cosmic microwave background spectrum, then what we find is simulations show that those initial clumpings of dark matter can seed the formation of ordinary matter clumping into galaxies and superclusters over time around those. Any more questions about that? Somebody want to ask another question? Okay, I saw your hand first.
When talking about conservation of angular momentum, why does that explain why a collapsing cloud forms a protostellar disk?
Why a collapsing cloud forms a protostellar disk, yeah. So the reason is, so first of all, as the cloud collapses, so that mass is getting closer to the eventual axis of rotation, what's happening to the moment of inertia of the cloud as it collapses? Moment of inertia, remember, is a measure of how far mass is distributed from the axis of rotation. So as it collapses, the moment of inertia is doing what? Increasing, decreasing, staying the same.
Or increasing, right?
So if it's coming together, and moment of inertia is a measure of how far the mass is, it's decreasing, right? Like, if I'm like this, my moment of inertia is large. If I pull my arms in, my moment of inertia is going down. And so what happens to the rate of rotation or spin as a result? Because remember that the angular momentum is given by this formula that says that the angular momentum, which strangely enough is L for the symbol, 2pi times the moment of inertia times the rotation frequency, the number of revolutions per unit time. L stays constant, so if I is going down, what's happening to the rotation rate?
It's moving faster, right?
It's rotating faster, yeah. If I is going down, and I times F has to stay the same. If I is going down, F has to go up in order to compensate. So as the cloud collapses, I is diminishing. That means F is going up. It's spinning faster. So it's similar to skater brings in their arms, and they spin faster and faster as they do that. Their moment of inertia is going down. The rate at which they're spinning is going up. So the cloud of gas collapses, and that makes it easier for material, if this is like the axis of rotation, that makes it easier for material to fall downwards along the axis of rotation than it does for material to move in perpendicular to the axis of rotation. I mean, imagine you're spinning and you're holding a weight going like this. What's going to be easier? If I'm holding a weight like this and I try to pull it in versus I'm holding a weight below or above me, what's easier? I'm spinning really rapidly. Is it easy to pull the weight in this way? What's your intuition? No, it's actually very difficult to pull the weight in that way. Whereas if it's just below you or above you, ignoring Earth's gravity, of course, if it's above you, like that, just like, oh, bonk, you know, but ignoring that part. Do it in space. It wouldn't be nearly as hard to pull the weight along your spin axis as it is perpendicular to it. And that applies to the cloud as well. So in other words, it flattens out because material can fall in more easily along the direction of the axis of rotation than perpendicular to it. And so it flattens out into a disk as a result of the fact that it's spinning faster due to angular momentum conservation. Any follow-up questions on that? Yes?
Can you discuss like the curvature of space-time, like as it's related to general relativity?
Right, so in general, according to general relativity, gravity is curvature of space-time.
Okay.
That is what gravity is. And so we saw different examples of that when we were talking about black holes. I mean, Earth's gravitational field is the curvature of space-time around it. That applies to Earth as well. For a black hole, it's more extreme. And so for a black hole, the curvature, if you were close enough to it, would have very noticeable effects. The analogy that is used, it's just an analogy, is the idea that you can think of a gravitating body like the sun or a planet or a black hole as warping the space-time around it. It's just an analogy because this is space-time being represented by a two-dimensional sheet, and the space is really three-dimensional, and you'd have to imagine curving the three-dimensional space. Humans can't visualize that, so we use this two-dimensional analogy to show the idea. And so light follows not straight paths, and planets follow not straight paths, and so forth, because they're moving as straight as they can, but they're moving in a curved space-time. That's what it comes down to. They're moving through curved space, and that causes them not to move on a classic straight line path, so that, for example, in black holes, we can see gravitational lensing. We can see distortions of images behind, of things that are behind black holes because the photons are not following straight paths to our eyes, and as a result, you get so-called gravitational lensing, bending of the paths of light. And then the universe as a whole can have an overall curvature due to the average density of matter and energy within it. But it turns out that the universe overall, when you include ordinary matter, dark matter, and dark energy, the overall density of the universe is essentially, as far as best we can tell, equal nearly to the critical density, so overall the universe is flat, as a matter of fact. Yeah. Any more questions about that?
What would a question about that look like on the exam?
Well, it's going to be 100% multiple choice. So, I mean, there's various forms it could take. I mean, you know, there's various forms it could take. But basically, all the questions will be multiple choice questions. So you're not going to have to like write essays about something. But you need to be able to recognize right answers from wrong answers when you see them, like usual for multiple choice questions. Yes?
Can you please go over the discovery that the astronomer made that worked with OWU?
Mm-hmm. Yeah, so she wasn't working with OWU per se, but she used our telescope, the original Perkins Observatory telescope, not when it was still in Central Ohio, not when it was down the road, but when it was at the mountaintop in Arizona, Kitt Peak in Arizona, Lowell Observatory. And so here she is, Vera Rubin, and what she did was use our telescope along with a spectrometer in order to measure the speeds of H2 regions in the Andromeda Galaxy, and thereby to plot a rotation curve, a plot of how fast things were moving in their orbits versus how far away they were from the center of the Andromeda Galaxy. She used Doppler shifts in order to measure how fast things were moving towards or away from us. So the idea is that a spiral galaxy, like our own galaxy or like the Andromeda Galaxy, is rotating because things have to orbit the center in order not to fall in. And so stars, gas, and dust revolve around the center of it. And if the galaxy is spinning as indicated, say this is the Andromeda Galaxy, if it's spinning as indicated, then this side of the galaxy is being carried towards us. Objects in it are being carried towards us by the galaxy's rotation. Over here, things are being carried away from us. Just like, you know, if I'm spinning, and here's my hands, right? My right hand is moving towards you because I'm spinning. My left hand is moving away from you. So, measuring Doppler shifts of gas clouds at various distances from the center of the Andromeda Galaxy, red shifts on one side, blue shifts on the other, she found that, surprisingly, the rotation curve is essentially flat. In other words, once you get past the inner region where there's an initial rapid increase in revolution speed with distance, past that, it's very nearly constant, very nearly true that all the stars, gas, and dust are moving at the same speed as you get further away from the center. And if all the mass were concentrated in what we can see, the stars and gas, we would expect something not exactly like, but more similar to what happens in the solar system, where because all the mass is concentrated in the sun, you get Kepler's third law, where the further away a planet is from the sun, the slower it is moving in its orbit. We don't see that at all with galaxies like our own, and Andromeda being another example of that. The first one was systematically studied by her, but then she studied others, and then other people studied others. Instead, we see flat rotation curves, and that implies that there's a lot of mass that we can't see because things out in the outer parts of the galaxy are moving faster than they would if all the mass that was there was the mass that we could see in terms of stars and gas. And so that's the fundamental discovery that she made using the Perkins telescope. Yes?
Can you go over Hubble using the secret variables?
Yeah, Hubble, using Cepheid variables in order to discover that, as many astronomers suspected, but others did not think was the case, that there is not just one galaxy in the universe, that the so-called spiral nebulae are other island universes, quote unquote, not literally universes, but in other words, that our galaxy is just one of many galaxies in the universe. And so Hubble made that discovery by, I keep it, what chapter is it in? I guess it's 22, is that one? Is that true? Which one's it in?
20.
20, okay, I'm not seeing the slide here, 20, I'm being blind. Oh, there it is, I'm just being blind, that's why. Okay. Yeah, so what Hubble did was observe the Andromeda Galaxy, and these are Hubble Space Telescope photos of this Cepheid, but this is the Cepheid that Hubble discovered in the Andromeda Galaxy, the first one, he found more than one, that allowed him to determine, that allowed him to determine that the Andromeda Galaxy is much too far away to be part of our galaxy. So he found a Cepheid, and remember that Cepheid variable stars have a distinctive relationship between their periods, in other words, how long they take to go from brightest to dimmest back to brightest again, and their average luminosities. They're thousands of times brighter than the sun, so we can see them for millions of light years. We're able to see individual Cepheid variables in galaxies that are millions of light years away. When Hubble was making these measurements, we didn't know how far galaxies were away from us, but he found a Cepheid in Andromeda, measured its period, and from the period luminosity relation determined its luminosity. And then he used the inverse square law to determine how far away Andromeda was. And the number he got was too small, but it was still big enough to say that there's no way the Andromeda Galaxy is part of the Milky Way galaxy. It had to be a separate galaxy from our own. And so that resolved the debate among astronomers, some of whom thought that there was only one galaxy and others who thought that there were galaxies throughout the universe. And of course now we know the ones who thought that there are galaxies throughout the universe were the ones who are right. Our Milky Way galaxy is just one of many galaxies in the universe. Any questions about that? Follow up. Okay, any other questions then? I'm going to guess yes. Yeah.
Could you maybe talk about what to look for when we see a picture of a galaxy and how to know?
Yeah, so you'd want to be able to basically recognize the different major types of galaxies when you see them, which isn't really terribly difficult. So that's chapter 20 again, right? It must be.
Yes.
Yeah.
Right. So basically, you'd want to be able to, let me turn the lights down again, maybe extra more there. You'd want to be able to tell the difference between, first of all, big picture, elliptical galaxies and spiral galaxies. Now, ellipticals are subdivided E0 through E7, depending on how flattened they are. I'm not going to worry about you looking at it and saying if it's an E5 versus an E3 or something like that. But in other words, if you see a galaxy which looks pretty much spheroidal or ellipsoidal and it's reddish in color, that's an elliptical galaxy. Whereas if it's bluish in color and looks like a pinwheel, it's got spiral arms, that would be a spiral galaxy. And spirals are distinguished between normal spirals and, I'm going to sneeze, so hang on here, or at least I've got that thing going where you think you might sneeze, which I hate because then it'll like go away. Anyway, but okay, anyway. normal spirals and barred spirals, and as the name implies, a barred spiral has a bar through the middle of it, a bar of stars through the middle of it, whereas a normal spiral does not. The nucleus is just more round in shape. And then the spirals are subdivided into A, B, and C, where if it's a very broad-looking pinwheel with a small nucleus, it's a C type. So like this is an SC, means spiral C, SBC, bar spiral C. So if the arms are really opened up like a nice broad pinwheel, that's C. If they're very tightly wound, that's A, and if they're in between, that's B. Now, you know, again, I wouldn't just give you a picture and you're supposed to know whether it's SA or SB. I'd have you like, you know, if there was like a comparison between the two, you know, you could tell me which one is which, that sort of thing. And then there's also irregular galaxies, which kind of look like blobs. Some of them look somewhat spiral in structure, but in other words, if it's not elliptical, not spiral, it's irregular. And then there's the so-called lenticulars, where they have disks, but they don't have spiral arms, and they don't have much in the way of gas mass in them. So basically, just visually be able to recognize those sorts of characteristics.
Okay, thank you.
Do you currently think that the Milky Way is a barred spiral?
The Milky Way is an SBB. Yeah, so it's a barred spiral, and it's of the intermediate amount of winding. So the Milky Way is classified as S big B little b. So S big B, big S big B means barred spiral, and the little b means that it's kind of medium winding in between the A's, which are tightly wound, and the C's, which are loosely wound in terms of the spiral arms. So we orbit a spectral class G2 5-star in an SBB galaxy. Next question. Oh, guess we're done. I'm mostly kidding. Yes?
Can you explain why accretion disks around black holes and neutron stars emit X-ray?
Yeah, why do accretion disks around neutron stars and around black holes make X-rays? Ones around white dwarfs typically don't make X-rays. They'll make ultraviolet light and visible light. So tell me this. What's going to be hotter, the one that's giving off visible and ultraviolet light, or the one that's giving off lots of X-rays? X-rays, yeah. So accretion disks around neutron stars and black holes are hotter than accretion disks around white dwarfs, which is why they give off X-rays. And what makes an accretion disk hot in the first place is essentially friction. So the material is spiraling down in towards the compact object, the white dwarf, neutron star, or black hole in the middle of it. The reason that it spirals in is because of friction between parts of the disk that are adjacent, moving at different orbital speeds. If that friction wasn't there, the material would just keep orbiting and not fall in, and the disk wouldn't heat up. But Kepler's third law says the material closer to the object at the center is going around faster than the material further away. And so you get some friction because different parts of the disk are moving at different speeds, and that friction robs the particles of orbital energy, and that's why they go into a sort of death spiral in towards the center. Well, what's got stronger gravity? White dwarfs or neutron stars and black holes? Say it loud, say it proud. Neutron stars and black holes do. So which disks are going to be spinning faster? Ones that are orbiting neutron stars and black holes, or ones that are orbiting white dwarfs? Neutron stars and black holes. The material is spinning faster, there's a greater amount of friction, it heats it up more. And that's why they emit it. That's why they're hot enough to emit X-rays, basically. Because the material is rotating rapidly enough that the disk with friction heats up to millions of Kelvin, hot enough to give off X-rays. Yeah, what's the difference between a Doppler shift and a Doppler redshift and a cosmological
Also the
shift?
stretching.
Right, which is, and that's automatic because cosmological redshift is due to the stretching of space. It's because of the stretching of space, because of the expansion of
And then
the
the Doppler shift just stars moving away normally.
So an ordinary Doppler shift is due to motion through space, right? So remember the whole business of like, if a train is moving away from you, then that stretches out the wavelengths of the sound coming towards you because each individual wavefront is given off at a different location by the moving engine, right? So remember, we had that whole thing of the Doppler shift arises because of the motion of something through space. So I'll go way back in time to, it's probably the light and matter presentation. Yep. So if we're talking about a Doppler shift, then if I have a stationary train, then every wave crest is given off at the same location, so you just get nice spherical wave fronts spreading away, all with the same center. But if the train is moving, every wavefront has a different center because it's centered on where the engine was, or the bell was, or whatever, when it emitted that wavefront. So if the train is moving to the right, that stretches out the wavelength behind it, piles up, shortens the wavelength in front of it. So that's a Doppler shift. Now, as far as, that would be in the chapter 5 slides. As far as a cosmological redshift is concerned, then that is due to the expansion of the universe. So the idea is, it's kind of similar to if you were to draw a bunch of stripes on a sheet of rubber and then stretch out the sheet of rubber, then the stripes would spread out as a result of that. You can think of the wave crests of photons as being like stripes in space-time, and as space expands with the expanding universe, it stretches the wavelengths, it stretches the wavefronts apart from one another. More precisely, an analogy I like to use is all the waves are moving through space at the speed of light, but the space between them is expanding as they travel. So it's like if I had 2 ants on the surface of a balloon that I was blowing up, then even if the ants were crawling along the balloon at the same speed, they'd get further and further apart as the rubber between them expanded. And that's what happens to the wavelengths of photons traveling through an expanding universe. The wavelengths expand as the space that they're traveling through expands. That's a cosmological redshift. The reason we see redshifts of distant galaxies is not that they are moving away from us through space, it's because the universe has been expanding since the time the light was emitted, so that by the time it reaches us today, the wavelength is longer than it was when it was originally emitted by the galaxy long ago. And that's what's happening. It's not a motion of the galaxies through space. They're getting further of it from us because of the expansion of space, and that expansion of space is stretching out the wavelengths. That's a cosmological redshift. Any questions?
Could you?
I'll get you in a second. Go ahead. Could I? You
The steps in life of a low mass star.
Steps in the line of a low mass star, like the sun, for example. Yeah. So.
You just need to know like how it moves along the HR diagram.
Essentially, if you can identify the stages on the HR diagram, you're good to go. Yeah. So let me find it here. Stellar evolution. Yeah, I mean, if you're familiar with this diagram right here, what it's doing when, you're pretty much good to go. So if we look here, so the sun is being used as the example here. It's the life of the sun. So here it is. At this point, the sun is on the
It's amazing.
main sequence. And when the sun is on the main sequence, what is its source of energy? It is fusing what? Where? Hydrogen into helium. Yes, fusing hydrogen into helium. Where?
In the core.
In the core. Yeah, in the central core. So step 1, main sequence star, fusing hydrogen into helium in the core. But it's eventually going to run out of hydrogen in the core. And that's when it leaves the main sequence. And so when it leaves the main sequence, it's no longer fusing hydrogen in the core because the core is out of hydrogen. So it switches to doing what? It's still fusing hydrogen, but not in the core. Instead, it's fusing it where?
Shell.
In a shell surrounding the core. And it fuses it much faster than it ever did in the core because it turns out the shell is hotter than the core ever was. The star is not in energy balance then because it is expanding with time. The core is actually producing more energy that is coming out of the surface, and so some of the energy is being used to puff the star out. And so it first becomes a subgiant and then becomes a red giant. So that's the next stage. And keep in mind that giant stages are associated with shell fusion. So if it's a giant, it's fusing in a shell for a low mass star. So, so we've got hydrogen shell fusion becomes a red giant. And then there's a point here where it stops being a red giant. You get this tip, so to speak, of the red giant branch here. This point right here is where it switches to another source of energy. What is it? It doesn't totally switch, but in other words, it acquires another source of energy. What happens?
The helium flash?
Yeah, the helium flash. The core becomes hot enough, 100 million Kelvin, to start fusing helium. It does so explosively because the core is degenerate. And so there is no dependence of pressure on temperature for degeneracy pressure. And so once the nuclear reactions start, they go out of control because the core cannot initially expand because its pressure doesn't change. So it just gets hotter and hotter, the reactions go faster and faster. So you get the helium flash, which eventually reaches the core in a couple of minutes, makes it so hot that it's able to expand and cool down. And then the star moves over here. And at this point, it has two energy sources. So what are they? Helium core fusion and also hydrogen shell fusion, because once fusion starts in a shell, it keeps on going. So here we've got a helium core fusion star, which also has hydrogen burning in a shell surrounding the core. Is it a giant at this stage? No, it is not. It is not. It's only a giant when it's here and here. So it's bigger than the sun is now, but it's not considered a giant when it is a so-called horizontal branch or helium core fusion star. It's much less luminous than the sun was. As a red giant, the sun will get something like 2,000 times more luminous than it is now. As a helium core fusion star, it's more like 50 times more luminous than it is now. But eventually the core is going to run out of helium as well. And so the sun will become a giant for the second time. Astronomers give it the funny name asymptotic giant branch star. We give it the name in this class double shell fusion red giant. double shell fusion, so there's two shells fusing. What are they fusing? One shell is fusing helium, the other shell is fusing hydrogen. So the double shell fusion red giant is fusing hydrogen and helium. So again, when the fusion is all in shells, a shell or shells, it's a giant. If there's any fusion happening in the core, it's not a giant. So hydrogen fusion in the core, not a giant, it's a main sequence star. Helium fusion in the core, not a giant, it's a helium core fusion star. So keep that in mind. Giant shell, not a giant core. There's a core source of fusion. And when I say giant shell, I mean only shells. In other words, if there's any fusion in the core, it's not a giant. It works out that way. But then the fusion in the helium shell turns out to be unstable, subject to flare-ups that will blow the outer layers of the star off into space, producing a planetary nebula, although as I mentioned, I've gotten ambiguous signals of late in terms of whether the sun will make a planetary nebula. It may be more massive. You need to be a bit more massive than that to produce a distinctive planetary nebula. But either way, the outer layers are blown off into space by a series of so-called helium shell flashes every few 100,000 years. And then what's left behind is the white dwarf. The white dwarf is the burnt out core of the star. What's the white dwarf made of mostly? Carbon, because the carbon was created in the helium core fusion star stage, because helium fuses into carbon via the triple alpha process, right, via the triple alpha process. So, as we mentioned in class, there's a rhythm to this. In other words, I think of to myself, and even for a higher mass star, a given type of fusion starts in the core and then switches to a shell when the core runs out of that element. So for the sun and similar low mass stars, it's hydrogen core, hydrogen shell. Helium core, helium shell. And if you look at the diagram here, it's hydrogen core, hydrogen shell. Helium core, helium shell. Right? So, kind of get that rhythm into your head. Hydrogen core, hydrogen shell. Helium core, helium shell. Poof! White dwarf. I would think of it in those terms. And keep in mind that once a given type of fusion goes into a shell, it keeps doing it. So in other words, when I say helium shell, there's also a hydrogen shell outside of it, because once it starts fusing hydrogen in a shell, it keeps on doing that. So if you can handle that, you're good to go, is what it comes down to. So, how would that show up on the exam? Multiple choice questions that say, of all the stages in this diagram, which of course won't be conveniently labeled anymore, right? Which one of these stages is, what is fusing where in stage 6? Or in which of these stages is helium fusion happening in the core, that sort of thing. Yes?
So iron doesn't release energy through fusion or fission in a high mass star. Is it because that the high mass star is burning heavier elements that becomes the core later on?
Yeah, so, right, of course this is for low mass stars, but if we go to high mass stars keep going. The sun will never get past helium fusion. Its core will never get hot enough to fuse carbon. Not so for a high mass star. For a high mass star, things keep going, and eventually you get to the point where you've got a series of shells that are burning different things. Burning, again, remember, means nuclear fusion to us. So at the end of its life, and this is not to scale, the core is actually just this little region in the center. It's much smaller than the rest of the star. Then you've got a hydrogen burning shell, outside of a helium burning shell, outside of a carbon burning shell, outside of a neon burning shell, outside of an oxygen burning shell, outside of a silicon burning shell, and the silicon burning shell, along with sulfur, is producing iron. And then the star is doomed because iron does not produce energy whether you fission it or whether you fusion it, so to speak. In other words, iron's at the bottom of this curve, which is saying if I combine anything with iron, the result has more mass than the stuff that went into it. So you'd be actually converting energy into mass instead of the other way around. And vice versa, if it were to try to split into two atoms, into two nuclei, they would have more mass than the iron did. So that won't happen because it would require energy. So iron cannot serve as a fuel, and so then the star is doomed because the silicon burning shell keeps piling iron into the core, but there's a limit to how much mass a degenerate core supported by electron degeneracy pressure can support. The center of the star, the iron core, is essentially like an iron white dwarf held up by electron degeneracy pressure in the middle of the star. Once it goes above the white dwarf limit, the Chandrasekhar limit, gravity is going to win and it's going to suddenly collapse and produce a tremendous amount of gravitational energy turning into thermal energy, and that is what blows the star apart as a massive star supernova. Any questions about any of that? Yes?
Wait, so which one, which step begins, like, the beginning of a supernova, you said?
So for a massive star supernova, as opposed to a white dwarf supernova, which happens in binary systems, for a massive star, a single massive star, like Betelgeuse, will blow up by itself, because once the iron core forms, it keeps having iron added to it by the silicon sulfur shell outside of it, and there's a limit to how much mass that core can have before gravity will become stronger than pressure in it. And when that happens, the iron core collapses in a fraction of a second, and the gravitational energy released by the collapse of the iron core, it starts about the size of the Earth. A fraction of a second later, it's the size of a neutron star, kilometers instead of thousands of kilometers. That release of energy is what blows the star to shreds, is what's ultimately responsible for it going boom as a supernova. Only I would have to say the boom loud enough to obliterate everything around. So I probably should have done that. Turns out I'm not able to do that, which is probably good. Yes?
There's a couple of ranking questions on Western astronomy.
There's a what questions?
Ranking questions.
Oh, ranking tests.
Do you recommend that?
Much as I would like to say yes, my answer is no, I don't recommend looking at the ranking questions because I'm making every question multiple choice. And while I could in principle turn a ranking question into a multiple choice question in practice, no, I am not doing that. So I would say look at the, don't just look at mastering astronomy, you gotta look at the study guide too, but to be honest, your payoff in terms of mastering astronomy is looking over multiple choice questions. That includes in those like flash tutorials, because those have quizzes at the end of them, like several questions at the end. But some of the just plain exercises are multiple choice format, and so looking over those will likely have some payoff is what it comes down to. Yes?
So there's a lot of equations in the reading for the chapters, but on the study guide there's just that one that you have, and then maybe Kepler's third law is going to be really relevant, but are there any other formulas that you would?
Yeah, so, like other exams, in terms of the quantitative reasoning, I'm not particularly interested in having you plug a bunch of numbers into formulas in a calculator and come up with some answer. I'm more interested in you understanding what formulas mean in terms of if I change one thing, what happens? So back when we were doing F equals sigma T to the fourth, I was more interested in you knowing that if I double the temperature, that means that the flux increases by 2 to the fourth, or 16 times, than I was in, if the temperature is 5,732 Kelvin, what is the flux from the surface? That's, okay, I put it in my calculator, I don't really get much insight from that from the standpoint of learning what the equation means. So, you know, I would provide any formulas that you needed, but it would be things like that, recognizing if something is to the fourth power, then what happens if I double it? If something is 1 over r squared, what happens if I double it? It becomes 1/4 as big, that sort of thing.
Is it like you're just
So don't memorize formulas in other words. Yeah.
Wouldn't that only be the relationship between distance and luminosity?
That's distance and luminosity, yeah, the inverse square law.
Which is,
It's an inverse square law. So, you know, so the formula is that the brightness is the luminosity over 4 pi r squared. More importantly, the brightness goes like 1 over the distance squared. So if I double the distance, it's only 1 over 2 squared times as bright. If I triple the distance, it's only 1 over 3 squared times as bright, and so forth. That's really the kind of thing that I'm interested in you being able to do. Also, being able to read and interpret graphs, like in the Mastering Astronomy. And a lot of the things are there. You go, here's a plot, interpret this plot. You know, can you read a plot and make interpretations of what the graph is telling you? And the Mastering Astronomy has the examples that, if you look at them, those are the kinds of things I'll ask, because that's where I'm drawing my inspiration from, is the Mastering Astronomy. That's why I assign you in Mastering Astronomy, is, you know, practice interpreting graphs and so forth. I'll get you in a minute. I saw his hand just before yours. Yes?
Well, will there be multiple answers, multiple choice questions?
Everything will be a multiple choice question. The entire exam.
Multiple answers.
You got, yeah, there's a few of those. Yeah, right. I can detect the true sincerity in your saying nice when I said that, yes. Yeah, there are some, circle all the letters that apply in here, yes. There's not nearly as many of those as there are other types. So think of those as special treats. He's not amused. Yes?
Could you talk about inflationary hypothesis?
Yep. The inflationary hypothesis is that when the universe was a teeny tiny baby, so to speak, or at least when it's very, very young, something like 10 to the minus 34 seconds old to about 10 to the minus 32 seconds old, for reasons unknown, we think, because this would help explain a lot of things, that
it's chapter 22.
22? Yeah, the cosmology chapters are all, you know, it's all just kind of all together in my head, so I'll forget. Like, where did the book talk about that? Yeah. So the idea is that the universe underwent a brief burst of really, really extra rapid expansion, exponential expansion, so that in about 10 to the minus 32nd power seconds, an incredibly tiny amount of time, a region of the universe which started out smaller than a proton would end up bigger than our solar system is now, which is remarkable when you think about it. In 10 to the minus 32 seconds, something smaller than a proton becomes the size of our solar system. So the universe as a whole became very much larger in a very brief burst of this so-called inflation. It's called inflation because you kind of think of like blowing up a balloon. Everything got inflated in size. And it solves a number of problems, which I would have gone over in class, but I was in Ann Arbor. One of which is called the horizon problem. And that is the idea that, suppose I look at opposite directions on the sky. They don't even have to be opposite directions on the sky, but it's a little easier to understand that way. I look in this direction, I look in this direction at photons coming from the cosmic microwave background. Did you have something you wanted to say?
Oh, is it like, at one point they had to be so, like, why are they so similar? Because they had,
Right.
they had to be extremely close, and they just got blown apart.
That's the idea, yes. They're about, all parts of the cosmic microwave background are essentially the same temperature to very high precision. There's very slight differences, but very slight differences. And so it's the same temperature in every direction. And the thing is that if you don't have inflation, those parts of the universe on opposite sides of the sky would never have been talking to one another ever since the Big Bang. They would have never exchanged any information or energy with one another. So there's no reason they should be at the same temperature. And as Charlie was basically saying, inflation explains that by saying that while they haven't been talking ever since inflation, if you run the clock backwards, if you go backwards, then you can think of the universe was a lot smaller before inflation than it was after inflation. So before inflation, those regions were talking to one another, were exchanging energy. Then inflation ripped them apart from one another, so they would never talk to one another again after that. But they were talking before inflation, and that's what made them come to the same temperature, so that we see them the same temperature today. And then there are other things it solves too, like for example, as we mentioned, the universe is very close to being flat. It's hard to explain that. It probably can't be a coincidence. And the idea is that the inflation would naturally take a universe which started out anything but flat and make it appear to be flat in regions the size of which we can see. Think about the surface of the Earth. Flat Earth society folks aside, eye roll, does the Earth appear to be flat to us? No, it's actually a sphere, but when you're on the surface of the Earth, as opposed to looking at it from orbit, flat Earth people, when you're on the surface of the Earth, the region you can see is pretty close to being flat, because it's a small part of a much larger curved surface. Inflation would say the part of the universe that we could see today looks flat because the universe as a whole may not be, but the region we can see is a small part of a much larger universe, and so the region we see looks flat, even if the larger universe on much bigger scales is highly warped. The part we can see looks very flat. The inflation would explain that. And then, well, those were the two things I was putting on there. The flatness problem and the horizon problem, are solved by inflation, essentially. So we haven't proved that inflation happened yet, but there is evidence for it in the pattern, in the fact that the universe is flat. It's hard to explain that any other way. Yes? So, so the density of the universe, when you include dark matter, dark energy, and ordinary matter, is very close to the critical density. And general relativity basically predicts that there is an average density of the universe that we call the critical density that would make the universe flat. And if the average density is more than that, then the universe would be spherical in shape. Less than that, it would be saddle-shaped. And the idea would be that inflation would drive the density of the universe, whatever it was before that, it would drive it towards the critical density by flattening out the universe. And when we add up, when we do the math, so to speak, well, that's not what I was going to say. Basically, inflation would drive the density towards the critical density so as to make the universe flat when it stretched things out.
How would the universe be different if it wasn't flat?
We wouldn't be having this conversation because it's possible to show that any deviation of the universe from flatness becomes worse with time. In other words, suppose when the universe was 1 million years old that the density was twice the critical density. Then, how do I best want to say this? There's different approaches I can take. Yeah, let's put it this way. For the universe to be as close to flat as it is today, it would have to have been extraordinarily flat early on in its history. And the best way to explain that is that inflation forced it to be extraordinarily flat very early in its history. Because you can show that if the universe was even slightly curved early on, then it either would have very quickly recollapsed long before life had time to form and wonder why the universe had the properties that it does, or if the universe was less than the critical density early on to any significant degree, it would have expanded rapidly enough that galaxies wouldn't have formed and we wouldn't be here to have this conversation. So essentially, the flatness of the universe appears directly tied to the idea that it lives long enough and has the right properties to form large-scale structure and smaller-scale structures compatible with us being here. I'm sorry, say that again?
We just don't know what the conditions would be like.
Yeah, we don't know exactly what they would be like, but to be compatible with us being here, it needs to be very close to flat, is what it comes down to.
So could you discuss the WIMPs?
The WIMPs, yes. So, dark matter, our best guess as to what dark matter is WIMPs, which is an acronym for weakly interacting massive particles. So in other words, the kind of matter that we're made of makes up some of the dark matter. We have observed black holes and white dwarfs and neutron stars, so-called compact objects, in the halo of our galaxy, but not nearly enough to make up most of the dark matter. Most of the matter that is needed to hold our galaxy and other galaxies together, but that doesn't emit light, or at least not very much light. So we need something else. We need something that would be some exotic type of matter that hasn't been discovered yet. Or we need to have some other explanation. So one idea was maybe neutrinos could be the dark matter, because neutrinos don't give off light. But the problem with neutrinos is they move close to the speed of light, and as a result, they would not be able to clump. And dark matter is clumpy. It needs to be clumpy to explain large-scale structure. When we map dark matter using gravitational lensing, it appears to have a clumpy distribution. Neutrinos simply move too fast for that. However, a particle which was similar to neutrinos in that it would only interact via the weak nuclear force and gravity, but was more massive than neutrinos, would fit the bill. The particles would be moving slow enough that they could clump together and would hardly interact with ordinary matter, which would explain why we haven't been able to see them yet, and would not give off much light. In fact, it would not give off any light, and so it would be dark matter. And so as a result, our best guess right now as to what the dark matter is WIMPs, some sort of, as yet to be discovered, weakly interacting massive particles, a sort of heavy neutrino, if you will. But we won't know what they are unless and until we actually discover them. Yes?
Can you go over the difference in location of convection and radiative zones in high and low mass stars?
Yeah, you know, what it comes down to is, in a low mass star like the sun, is it the core or is it the outer layers that have convection? Yeah, it's the outer layers. The sun's core is radiative, and the outer layers are convective in the sun. In high mass stars, more than about 1.2 times the mass of the sun, so that's not really high mass per se, but higher mass stars than the sun, it switches, and it's the core that is convective and the outer layers that are radiative. And that turns out to be for two reasons. One, higher mass stars are hotter, so the surface of a higher mass star has a temperature which you only find in the sun, not in the core, but further down where it's not convective, still outside the core, but not convective. So the higher temperatures of the outer layers of higher mass stars make them no longer convective. And the fact, it turns out that the CNO cycle is how hydrogen is fused in higher mass stars, makes the core convective, because it turns out the CNO cycle is really, really sensitive to temperature, and that turns out to make the core convective. So it flips. Higher mass stars have convective cores and radiative outsides. Lower mass stars have radiative cores and convective outsides. In either case, unless you get to the lowest mass stars, where they're convective throughout, the point is then that what's in the core stays in the core. The core is like the Las Vegas of the star. What's in the core stays in the core, and as a result, the star wastes most of its fuel. The sun will only burn about 10% of its hydrogen into helium, but that's the reason the sun will become a red giant someday. Is there will still be fresh fuel outside the core to allow hydrogen burning in a shell. That's why the sun and other stars become giants when they run out of central fuel. It's because there's still fuel to burn in shells outside. That's the key to that. Yes?
What provides the source of energy when the protostars shine?
Yeah, so for a star like the sun, what's the source of energy? Nuclear fusion, right. So full-fledged stars are powered by nuclear fusion. A protostar is shrinking. So what kind of energy is changing there? It's gravitational energy. Gravity powers protostars. They are powered by the conversion of gravitational potential energy into thermal energy and radiation. So protostars are gravity powered, so are massive star supernovae for that matter. They're gravity powered too, because the core collapsing does the same thing on a much more rapid time scale. It converts gravitational energy into thermal energy and radiation, but ultimately, a protostar slowly converts gravitational energy into thermal energy and radiation. We've crossed the magic threshold. Oh, that's it. I'm done.
See ya.
See you later.
Good, thank you.
Yeah, I know you're good. Yes?
Can you go over neutronization in a collapsing core?
Neutronization in a collapsing core. Yes. So, core is made of iron, right? First. As it collapses, it gets very hot. And so, the first thing that happens is that the gamma rays become energetic enough to break the iron nuclei apart into a bunch of helium nuclei. And as the density keeps increasing, and this is all happening in a fraction of a second, as the density keeps increasing, what happens is that electrons combine with protons, to form neutrons and neutrinos. And so the collapse of the iron core is accompanied by a tremendous burst of neutrinos that are formed when electrons combine with protons to form neutrons plus neutrinos. So the neutrons stay behind and are the neutron star. The neutrinos escape. But the neutrinos we think are important because even though neutrinos can easily pass through light years of lead, not that there's any light years of lead anywhere, but neutrinos hardly interact with anything. But the collapsing core is so dense that we think that the neutrinos do interact with it enough that computer models seem to indicate that the neutrinos are actually what gives the push that's necessary to start the explosion spreading outwards in a collapsing, in an exploding massive star. And it's interesting that, the Department of Energy has in the past funded a lot of the scientists who build computer models in order to model supernova explosions. You may be asking, why is the Department of Energy so interested in supernova explosions? And it's because the same kind of computer code that can simulate the explosion of a massive star core can be modified to simulate the detonation of a nuclear warhead so that we can numerically, so to speak, test nuclear warheads without actually having to detonate them, which is forbidden under test ban treaties unless you're North Korea, in which case you don't care, is what it comes down to. So fun fact for the day.
This is unrelated to the test, but I saw in Wall Street Journal or something that there's some new kind of matter discovery recently.
I guess I missed it. You have to send me the link. Yeah.
Exitonium?
I have no idea what you're talking about, so I missed that one, so I'll have to look that up. It sounds interesting, but I don't know anything about it. It sounds exciting.
Sounds fake. You don't know.
Yeah. So then years from now, I'll be nostalgic and I'll be looking at this video and I'll be like, look at that. I hadn't even heard of exitonium yet, and now it's the basis of our economy.
They probably wouldn't be economically.
Probably not. Although that's what they said about electricity too. Wasn't it all obvious that electricity originally was like a toy at parties and stuff like that. Nobody thought it was going to be particularly useful. Oh, thank you. You're welcome. Apparently there was like a study in the 1950s that had estimated that the United States might need as many as 6 computers at some point. You're welcome.
See you tomorrow.